Thank you for the introduction. With me, Shivram Rao and Dibendu Das are the co-author of this paper. So, loop unswitching is a well-known compiler optimization. It moves the condition inside the loop outside by duplicating the loop body and places the appropriate version inside if and the else clause. And efficient unswitching is severely inhibited in the cases where the condition inside the loop is not invariant or probably partially invariant. By partial invariant, I meant it is invariant in few parts of the loop body, not invariant in all the parts. A loop containing loop invariant if statement can be transformed into if statement containing two loops, as shown in the below example. So on the snip 1, there is a loop which is iterating from 0 to n, and there's a if condition inside it, if x. So when this condition is true, it executes ai equal to 0. When it false, it executes bi equal to 0. So this can be transformed into the unswitched form if only if when if condition is invariant. So the right hand side shows the unswitched form where if condition containing two loops, each in the if and the else clause. So this not only moves the condition outside, it's open up for the further optimizations. So here it completely dependent on the loop invariant property, but what if condition inside the loop is not invariant or partially invariant? So loop unswitching is inhibited in the cases where the condition inside the loop is not invariant or partially invariant. Loop unswitching can be still applied on the cases where the condition is partially invariant. By generating the improved version for the invariant path, and the original path will have the complete loop version with all its conditions. A partial invariant is an expression, the value of which remains same immediately before and after each iteration of a loop in a certain path. So here P invar is the partial invariant, where I is the invariant and P is the path where this condition is invariant. Identification of the partial invariant is a prime task in our work. Note that only a portion of the original loop may be controlled by the property of interest. So partial invariant identification is very similar to the loop invariant identification, but scope is limited to the certain paths. So for this, loop analysis is required, and this analysis will explore different paths in the loop and figure out what are the partially invariant in which paths. Existing LLVM existing invariant analysis framework does not identify partially invariants. It is bound to full loop invariant conditions. A simple version of path invariant detection is applied. Focus on the branch condition at certain levels. So where the path or the condition of a branch is a subtree starting from either of its successors. So here this example shows what are the possible paths at a certain branch level we are considering. So here is a C snippet where the iteration range start from start and going up to end. It had nested ifs, but as I said earlier, we are considering a branch at a certain level. So here we are talking about the top level branch. So it is dependent on a variable cont. So here there are two possible paths. First, starting from cont and going when condition is true, it is taking the first or the left path where the if x is there and follow it has multiple blocks, and at the end it goes to S6. When the condition is false, it goes towards if y, and at the last it executes x6. So here one point to note is S6 is an overlapping block here. So here our path of interest is only two, left path or the right path. So we'll apply the classical invariant detection techniques on these to figure out in which path our condition is invariant. So here are a few examples for the partial invariant detections. So condition is explicitly modified in a path implies it is not an invariant path. So in this example, in the true path of the condition is explicitly getting modified. So if then clause is not a path of partially invariant. Same applies to the if else clause. Condition is not explicitly modified in a path, then it might be an invariant path. So in this example, condition is only explicitly getting modified in the if then clause. In the if else clause, it is not getting modified. So the else clause may be an invariant path provided the other conditions are met. Varying condition in loop body in each iteration. So here there is a very simple example where condition is dependent on the induction variable. It is varying on each iteration. So of course this cannot be a candidate for partially invariant. Condition dependent on a varying variable in the loop body can be partially invariant for a path where the variable v remains unchanged. So in this example, variable v is getting modified in the if then clause, but it is not getting modified in the if else clause. So it may be invariant in the if else clause. So one point to notice here is in the first iteration of the loop, if the control goes to the else clause and v is not getting modified in the else clause, means it will always execute the else clause. It will never execute the if then clause because the condition is not changing. Of course, function call can modify the condition values. Let's say a condition is a global variable and a function call is made. So in such cases, those function calls can modify the condition values. Or an address of a condition is passed to a function. Those condition is exposed outside, so those calls can modify the condition. So we have to be a little careful with the function calls here. Control flow guarantees that at runtime loop will always execute the non-modifying path or the invariant path. It will never execute the variant path. So in this example, if you see the else clause, the condition is not getting modified. So we can say that in the else condition may be invariant, but there's a catch here. There's a go to L1, and in the L1 block, the condition is getting modified. So of course, in the else clause, condition is variant. Non-explicit modification to the condition can change the program behavior at runtime. So in this example, in the else clause, there's no explicit modification to the condition, but there's a store to a pointer. So what if this ptr alias with the condition? In such cases, it will modify the condition, and in the runtime, the control flow will switch from the varying branch to a non-varying branch. So I'll summarize. These are the few key things for the partial invariant detection. So as I said earlier, we have applied the classical invariant detection techniques. So I just listed down the few key things. So condition is explicitly modified in a path implies it is not an invariant path. Condition is not explicitly modified in a path, then it might be an invariant path. Condition in the loop body may depend on an induction or reduction variable, and it may change and it may switch the path at runtime. Condition dependent on a varying variable v in the loop body can be partial invariant for a path where v remains unchanged. Function call can modify the condition value. Control flow should guarantee that at runtime, the control will only execute the non-varying path, non-modifying path, and it will never execute the modifying path. Non-explicit modification to the condition may change the path at a runtime. So this is all for partial invariant detections. Once we identify the partial invariance, the next step is to use the partial invariant. So we have used this partial invariant in the partial loop unswitching. So partial loop unswitching is an efficient technique to unswitch partial loop invariant condition. It identifies the partial invariant condition for a path and it moves the condition inside the loop to outside by duplicating the loop body and placing the version in each if and the else clause. The varying path will have the full loop version with all the conditions, whereas the non-varying path or the invariant path will have the improved version. So here is one example. In this example, there is a loop which is iterating from 0 to n, and there is a condition if x, when this condition is true, it does ai equal to 0. When this condition is false, it updates the induction, it updates the condition variable, and it sets bi equal to something. So here, one thing probably we can deduce is, in the if-then path, x is not getting modified. If it is not getting modified, it is a candidate for partial loop unswitching. So how the partial loop unswitching or how partial unswitched loop will look like? On the right hand side, first we'll do the loop execution guarantee check because we are moving the condition outside. We have to ensure that it is safe to execute that condition. So loop execution guarantee check does, it just ensure that it is safe to execute. It does the bound checks and it executes the condition. So after that, how it looks like is, we have translated it in a way that if condition containing two loops. So if x is true, in that case, there's a loop which does ai equal to 0. When x is false, in that case, we will execute the complete loop with all the conditions. So by doing this, we have translated in unswitched form, and we have opened this for the further optimization. If you see in the first loop or the improved version of a loop, we can do a memset here. So this is few details of the implementation framework. It is categorized into two categories. First is the partial invariant analysis. Second is the partial loop unswitching. So goal is to identify partial loop invariant condition for a path in the loop body. We have implemented an analysis utility in LLVM to identify the partial invariants. Then once we identify the partial invariant, we will deploy this information in the partial loop unswitching. Goal is to transform by generating an unswitched version for the partial invariant cases. We have extended the existing LLVM loop unswitching framework for this. So this is few glimpses about how LLVM existing loop unswitching translate a loop to an unswitched form. So in this, there's a C snippet. There's a loop which is going from start to end. There's a condition inside it, and the condition is not getting modified in either of the clauses. So of course, the condition is a loop invariant condition. So this will be transformed into a if condition containing two loops. So this whole process will be done in the two steps. First step is just duplicate the loop body in both the clauses. Second step is just remove the condition by setting the appropriate true or the false value. So in the this is the first step output where we just duplicated the loop in both the clauses. So in the second step, replace condition with true or the false value in the appropriate versions. So here we have replaced in the first part of the loop, we have replaced the condition with true, and in the second part of the loop, we have replaced the condition with the false. So this is how the transform loop looks like after loop unswitching. So here I comes to my extension to loop unswitching. So in this extension, of course, we are dependent on the path invariance information. That is a separate utility. But after that, how we will transform the loop and how exactly it will look like. So step 1 remains same. It means that if we identify some partial invariant, we'll just duplicate the loop body as existing loop unswitching does. In the second step, what we'll do is in the path where the condition is invariant, in that path we'll just replace the condition with either true or the false value. So in this example, in the else clause, condition is invariant. So we have replaced the else clause. We have replaced the condition, the if condition with the false value. So thus we have got this version of a loop. So this is some high-level details about how we are identifying the partial invariance. So how it looks like, you have a loop has a header block. In the end of a header block, you have a condition, and that condition is further going to the multiple blocks. So we'll start with the condition. We'll just check what are the dependent instructions of this condition. So the dependent instruction could be memory accesses or a fee node. So we'll just preserve this memory access somewhere. In the second step, what we'll do is we'll just check the condition is really getting modified in the header block or not. It is safe to consider it as it is a safe instruction, it is a safe condition or not. If it's getting modified, means it is not a invariant condition. It is a variant condition. If it is not getting modified in the header block, then the third step comes where we'll just start with the successor of the branch instruction in the header block, and we'll traverse the subtree. So here the path checking starts. So we are starting with the header block successors. So we'll take the first successor, and the subtree below is a path first, and so on with the second successor. So we'll go up till the exit block and check whether this condition and its dependent instruction is getting modified or not in between. So how it works is we'll just take a block and we'll just iterate all the instructions of a block. If that block is a loop exit block, we'll simply return. If it is not an exit block, then we'll iterate over all the instructions and check the condition safety. So there are few things I mentioned here. If the instruction is a write to memory, then the return address should not be the condition or should not alias with the condition. If there's a write to memory, then the return address should not be or alias with the condition dependent memory accesses. Condition dependent on a fee node should not be affected by a write to memory in the path. If there's a write to memory in the path, it should not feed the fee incoming. If there's a call instruction, then it should be a safe call. By safe call, I meant no indirect calls. Call function does not access the memory, or it's a read-only call. For branch instruction, all the successor repeat step 3a. So this further traversing to figure out the condition is variant or not. So by this, not all the details are kept in this slide, but here the top few key details are kept. We're trying to figure out condition is invariant in which path. So once we identify the invariant condition and in which path it is invariant, then we'll deploy the partial loop unswitching. So how it works is we have extended the existing loop unswitching. Existing loop unswitching, and how it works it just look for loop invariant, and try to move all the loop invariant outside the loop. So it has its own profitability and it has its own legality checks. So once all the loop invariant are moved outside, then it simply exits. So at that time we'll take the control And what we'll do is we'll just do the legality check. So by legality, it's a lightweight check. What it does, loop should have a very simple form, means it should have a pre-header, exit block, and a latch block. We are just checking these three things. Then if loop is in the proper form, then we'll invoke the partial loop invariance analysis to figure out if there any partial invariance exists in this loop or not. If any partial invariant exists, then in that case, we'll do the profitability check. So profitability checks is try to predict how your code will look like, how big it is, what are the instructions you are moving outside. So if it is really profitable, then we'll do the transform. We'll invoke our transform, and it will do the unswitch for the invariant path. Once this is done, then we'll just go to the, it is just like a loop, we'll just go to the existing loop unswitching. If it may open the cases for another loop invariant conditions. Once there's no loop invariant or there's no partial invariant, we'll come out of this transform. So with this, we have observed 1.07x uplift in spec 2006 Omnet PP. We didn't, there's no impact on the other CPU 2006 benchmarks. With this, we have observed other gains in our internal benchmarks and applications. So with this, I summarize the cases where loop unswitching is probably the loop unswitching is if there's no possibility of a loop invariant. On such cases, we'll try to figure out if there's a partial invariant, and for the partial invariant and the associated partial invariant path, we'll do the unswitch. This I'm open for questions.
So, thank you. Are there any questions?
In the path invariant version of the loop, when you then, in the path variant version, when you then enter the invariant path, why do you continue executing the loop that has the condition? Why not just transfer to the other version?
Okay, so the other version should have the complete version, because in the other version, path switching is possible.
So once you've taken the branch, that means you can no longer go on the other branch.
So for that path only we have done the unswitching, but for the other version we should keep the original loop intact, because in the original loop the path switching is possible.
Sure, but it's only possible on the path switching path. As soon as you go into the non-path switching path, surely then it's invariant. And you so you should then switch to the invariant version straight away, rather than only checking that condition on the first basically iteration of the loop.
Yeah, so for the invariance, the prerequisite, there should not be any path switching. If there's a path switching, then it will enter a path where the condition is getting modified. So that is a prerequisite for partial invariant.
Yeah. So might have duplicated a question here, but I was going to ask, it seems like what we've got here is we've got a portion of the iteration space where we have a condition that is invariant. And it felt really odd to frame this as loop unswitching as opposed to some form of iteration space splitting, and to have a pre-loop and a post-loop that sort of the post-loop running the version that the condition is invariant. I was curious why you chose unswitching as the transform rather than a form of index splitting.
Okay, probably I didn't understand your question properly. So your question is why this is a good fit for unswitching.
Maybe go to the example.
This one?
Yeah. So in the second version of the loop, where you set AI to 0, from that point on, you are basically in the first loop. So the second usage of AI to 0, that should go to the first version of AI to 0. one iteration, the first one, is the variant path. Once you hit the second one, you are now in the second set, so you go to the optimized version. It seems like you find this split, but you only check it on the first iteration rather than every iteration.
Yeah, I mean, here the understanding is if it execute the first iteration in the else clause and the condition is not getting modified in the else clause.
So let's say on the second iteration, now x is true.
So it means that it is switching.
But it cannot switch back. Once you hit the invariant path, once x is true, x can no longer be modified.
So in the switching cases, we should preserve the complete loop.
Saying is that you can have some number of iterations where maybe the condition is modified, but once you hit an iteration where the condition can no longer be modified, then from that point on the condition will never be modified.
Okay.
And so you can think about it as splitting the iteration space, where the first few iterations maybe the condition might be modified, but once you get to a iteration where the condition will not be modified, you can stay in that part.
Yeah, it's a good
So
point.
that's why it's index set splitting.
It's a good point.
Index space splitting.
Now the induction variable is not at the beginning anymore. In this case, I is not declared there. So you have to, the mechanics that you have to do is not simple, and you have to make sure that it counts. Yeah, exactly, yeah. Oh, in this simple case, yes. Well, a go-to there will just fix everything. Yes.
And you really always do this because both loops are following the same induction variable.
Yes, yeah. Wait, so yes, in this very simple case, it would work very simply. But
So that would be my sort of other follow-up question. Is this a more general transform than we're seeing in this example? Are there cases where forming it as the index set splitting wouldn't be correct, but this formulation would still trigger? Are there more complex examples than the ones you're showing here?
Want to answer this?
Sorry. When you ran your benchmarks, did you actually look at how often the unswitching actually happened? How often you took the optimized path?
Yeah, so in our analysis, we have did where exactly it is kicking and how it is beneficial. So we have seen some cases where this is opening up opportunity for the vectorization. So with the condition, of course, you cannot do the vectorization. So once you move the condition outside, you can open the things for the further optimization, probably vectorization or dead code elimination.
Okay, I have another question. It seems that we always preserve the original version of the loop. How do we ensure that in a more complicated case, this original version and this condition will not again be recognized as partial invariant, and we unswitch it again and again and again and go to infinite recursion?
So this is based on an understanding where if you execute the unswitched path and there's no possibility of path switching. So if this is the basic thing for it. So if the path is not switching, in that case, the first loop will execute, or the improved version of the loop will execute. And if there's a possibility of path unswitching, right? So you have to preserve the semantics. For that, you have to preserve the complete loop.
I think you didn't answer the question, but I think, so I'll just rephrase, and you can correct me if I'm wrong. I believe he was asking, what prevents, if you take the transformation, loop unswitching, and you ran the transformation on the same code multiple times, what prevents it from triggering on the original loop again and again and again and again? So you keep versioning the loop. Is that what you were trying to ask? Okay, yeah. Do you add metadata to the loop or something to keep the loop unswitching from continually unswitching the non-unswitched version?
So unswitch.
Yeah, that may be true.
So unswitch actually does the same thing. It is called in a loop to move all the invariant condition outside. And the main, if I understand correctly, their main focus is to remove the condition and open it for further optimization. So of course the multiple
Right.
version will get generated.
Okay, but then if you ran unswitching again,
No, no. I mean, for the same loop, it will generate the optimal version. Is that you're trying to ask?
Yeah, so, right.
So, I mean, we have taken those things into consideration. We set some metadata and ensure that for this already you have a version generated, and
Okay.
those things should be taken. Those
Sure.
things are taken care of.
Yeah, okay, that's what I thought. I just want to ask you, so maybe you mentioned this at the beginning and I missed it, but are you planning to contribute patches for this?
So we have done a very basic implementation. So we have yet to improve it. I mean, there's so many cases we have seen where this is not kicking in. We are generalizing it. So once this comes in a good shape, then probably we'll think about it.
Okay.
Are there more questions? Okay, then thank you again.
Thank you.